All right, part 2 of the introduction to linear approximation differentials. And what we just got here was this dy equals this 1 over 3 x to the 2/3 times dx. So let's not lose sight of what this dy equals f prime of x dx is giving us. And remember, the differentials are based off of the tangent line, the linear approximation line. And if you think of that line as having a slope given by f prime of x, then the change in the y, the dy, the differential dy, could be found by just multiplying the slope by the change in x. This goes back to algebra. So for example, if your slope was 1/3 of that tangent line, you had a change in x of 7, the change in y over that span would be 7/3, 1/3 times 7. So that's all this differential is now relating, using essentially information related to that L of x line, that tangent line. So the change in y, always going to be this f prime of x dx. So using what we found in part A, I'm going to evaluate dy and delta y if x is 1, and then the dx, which is also the same as the delta x. Remember from part 1, talked about that. The change in the x is no different for the original function or the differential based L of x line. And both those, since they're equal, we're just going to say, well, they're going to be 1. So dy, differential change in y based off the L of x line, is going to be 1 over 3 times 1 to the 2/3 power, and then times dx, which is given as 1. And when you work this out, you get 1/3. Delta y, what we're going to do here is we're going to use the f of x plus delta x minus f of x to find this. So we're going to have f of x, which is 1, plus delta x, which is 1, minus the f of x, which is 1. So we really just get the cube root, that's the original function way up here, the cube root of 2, 1 plus 1, and then minus the cube root of 1. And when you work this out, you get 0.26. So if you think of the 1/3 as being 0.3 repeating, or 0.33, if you're rounding to two places, 0.33 is not a terrible approximation of 0.26. It's certainly off by some, but it's not a terrible approximation. And the closer you are to the original x, here we let dx and delta x be 1. If you were maybe dx equals delta x was 0.5, your approximation for the dy is going to be even better. So that's essentially all there is to differentials, using this new little form here where you have this dy equals f prime of x dx in order to calculate the approximate change in y based off of that L of x line. All right, thank you for watching.